did last time, we discussed the DPM implementation and also DDPM, which was the special case of DPM, right? So just a quick recap what we did. We had diffusion system or diffusion process. The idea is to just learn how to reverse the process of diffusion from image to noise, right? And then there had been a couple of approaches based on score. It didn't work. The one which worked was the one based on variational inference, right? And that one gave us a very concrete loss function that we could train in order to get one specific model trained to reverse the Markov chain, which is taking us from image to noise, right? And then that concluded the model. We called it diffusion probabilistic model, DPM. So the idea there was that this model is always a Gaussian, and you learn the mean value, right? And then that mean value was your neural network. You could simply use time sampling. This was the trick. So you don't really need to really go on the process. So you just randomly select one time in the whole diffusion chain, and then you train your model. This is one sample, and then you just do lots of sampling and train your model on the different time steps. Then this model starts to learn how to take you from one time step to another, right? And then that was the model DPM. And denoising DPM was the very specific form of it, where that mean value network was defined to somehow first learn the noise impact and then cancels it out, right? So this was the idea in denoising DPM. The main reason that it worked better was that you know the noise sample every single time because you are the one who is generating inside your data set, right? And this was the key point which made DDPM to work significantly better than the other models being trained before, okay? So we ended up understanding what was DDPM and how we can train it, how we can sample from it. There is, however, one tiny issue, and that issue is that if you use DDPM, potentially you could get very long sampling time. And you could simply see it on the sampling process, right? If I just train a DPM model, I basically am able to find out what is the noise process, the direct noise process, epsilon t, for a given time t and the noisy version xt. So I'm going to look at xt at the particular time t. I'm going to say what is the noise error that has been added to this to the original data, ending me up with this noisy sample, right? So I can do this. If I want to just do the denoising, I should start from the very last time step, which is eventually the noise sample, and then I gradually start to denoise, right? Every time I just estimate the direct noise, but then I use this direct noise to get one step back, right? And then I keep on going till I get to the beginning of time. This is the sampling that is happening in DDPM, right? Now, when you are training, of course, you can do time sampling, right? Because you are just training. So you sample one time, you add the direct noise, you have the noisy version, you have the noise, you have the time. This is one sample, you compute your loss, right? And you do lots of those sampling. But when you want to generate, you really need to go over time. So you need to start from Gaussian noise. You need to denoise every single step till you get your image, right? This is the way that you can do it. This t value that you see here, this capital T, is typically very large. So in the order of 1,000, right? If you check the DDPM paper, it's exactly 1,000. And then this whole thing could be very time consuming, especially if you are doing high quality generation, like images with very large number of, high resolution. So one point is that you cannot really train it. I mean, you can try it, but you can see that if you train it for a smaller period of time, like instead of 1,000 time step, you do it 500. And then you reduce it to 150. If you do that, then it starts to somehow get lost. So it cannot converge. And the main reason is that, I mean, if we keep this diffusion point of view from very beginning, what we are doing, this whole Gaussian reversion that we're doing, is working when those noisy steps are very tiny. If they are not tiny, then eventually there is no reason for your reverse process to be simple Gaussian. And eventually, it seems that it's not Gaussian, so it's not going to converge. So the point is that you cannot really make it converge when the time steps is very small. And then people initially thought this is a part of the fact that we have it, right? So we can do nothing about this. Maybe we can use some tricks, like, for instance, instead of just learning that noise, we also learn the noise variance that we are supposed to add it in every single time step. Those sigma values, which we kept them fixed initially when we were developing DPM and DDPM. Maybe you can think of them to be some learnable parameters. You try to learn them. And when you learn them, maybe this is going to help you to just converge better, and then you can reduce the time steps. So some tricks like that have been done before, but the key idea, which made it significantly shorter in time, is the idea of DDIM, which is implicit sampling. So it's a kind of deterministic way of sampling. So when you have your trained model, maybe you can use it to do deterministic sampling, and this is the idea of DDIM, which is quite intuitive idea. It's not like a very concrete mathematical idea, mathematics behind it, but this somehow works when you want to sample. So what is the main idea? So the idea in DDIM is that you would say, okay, if I am at the particular time t, and I have the noisy version xt, which is my original data, if you remember, added with some direct noise, right? So we always could write down at any time step, even though we are moving step by step in time. We said that we always can write everything directly with respect to the original data, right? So x0 got added with some noise, and then we are at time t, right? So we are estimating in every single time that noise, that direct noise, right? And if we just write down the noisy version in time t, xt, you would say, okay, there is one factor, alpha bar t, multiplied by x0, and 1 minus that factor multiplied with the noise, right? Now, if I do know what is this sample noise, epsilon t, if I do know that, I do have access also to xt, right? Can I estimate x0? Can I do that? Yes, I have the estimate of the noise. I just do the math, right? So I just take everything the other side. So I would say, okay, xt minus the scale version of the noise divided by the other factor, this is going to be x0, right? So supposedly that guy should be x0, but if you try it on very early steps, this is not going to work. So you don't get, you don't get really into your data sample. The main reason is that it's too noisy, right? That your estimate epsilon hat t is not very accurate, okay? So epsilon hat t is not accurate. It's a very, shallow estimate of the true noise. And because of that, when you just directly try to jump from that point of time to the beginning of time, then you are not going to get what you want, right? So it's not accurate, and the main reason is that this epsilon t estimate is not accurate. But DDIM idea is built based on that. It says, we do know that epsilon t is not accurate estimate in time for the direct noise, but maybe we can use this property to somehow get one step back in time, not by noisy sampling, not by generating some random Gaussian noise and adding it up. We just do deterministic sampling. So how we can do the deterministic sampling? So, well, I have this estimate, right? This is the estimate. This is exactly what I showed you in the previous slide, right? So this is epsilon w. This is the estimate given by my network, by my neural network, for the noise sample at time t. So I can just write down my estimate of the data sample in this form. The point is that if I know this estimate, and I don't care that this is a bad estimate right now, I can take this one and estimate the previous time step, right? Why? Because the previous time step, how can I write down the previous time step? Can you tell me? Xt minus 1, what is it? if I want to write it down in terms of the direct noise, I would say there is alpha bar t minus 1, right? Multiplied by x0, right? This is the direct link, right? Plus a square root of 1 minus alpha bar t minus 1 times epsilon t minus 1, right? Okay, I have this guy, not itself, but a very bad estimate of it, right? So I'm going to put it here. Everybody's clear? Okay, cool. So I am going to put that x0 exactly here. This is going to give me an estimate. But if I want to complete this estimate, I need to have one estimate of the noise, direct noise. Can I compute that that estimate of the direct noise? Do I have anything that I can do it with? What does the neural network do for me? It's estimating the direct noise, right? If I want to estimate the direct noise at time t minus 1, and t minus 1, right? So I can write it down in this form, right? I could say if I had xt minus 1, I would put it inside the neural network. I give also t minus 1 to my neural network. Then the neural network is going to estimate the noise, the direct noise at time t minus 1, right? And I put it here, right? Then this guy is an estimator of x hat t minus 1, right? Everybody's clear? So the only issue here is that I need xt minus 1 to do this computation here, but I'm actually computing xt minus 1, right? So I don't have xt minus 1 yet, correct? But there is one key point here. So I don't have xt minus 1 itself to compute this direct noise, but there is one key point here, and the point is that I can eventually estimate or approximate this epsilon t minus 1, epsilon hat t minus 1, with epsilon hat that I computed at time t, okay? Now, you might ask me why I can do this. So I don't want to open this up for you because, I mean, there is no real point in explaining this, so you can take this from my side. But just to give you a bit of idea why this is happening, so if you remember when we wanted to just approximate things at the beginning of this chapter, we had this issue that those differentials, d something that we had always some random thing inside it, right? There was Brownian motion, correct? And that Brownian motion was random, tuning everything. So that approximation was not the approximation that I can say differential of something is very small, right? So any equation of this form is always an approximation of a differential equation. But those differential equations that we had, they were SD, stochastic differential equations, right? But here in this equation, you just think of this green x hat t minus 1 to be xt minus 1 itself, okay? So you have xt minus 1 in terms of something here, right? And here x hat 0 is given to you because you already computed it. Xt minus 1 is unknown. So it's a kind of fixed point equation, right? Xt minus 1 equals to something in terms of xt minus 1, correct? Now, is this equation involving anything random? Is there anything that I generated randomly and I put it here? No, nothing. Because xt minus 1 is the guy that I want to compute. X hat 0 is eventually computed in this form. So I had xt minus 1. I gave that to my neural network. I got the noise, and I computed this thing, right? And then this is going to be the estimate. So this x hat 0 does not get added to any random Gaussian process I generated randomly, right? So this guy is not anymore a stochastic differential equation. This is somehow approximating an ordinary differential equation. And if you are doing ordinary differential equation, this is not a weird assumption that the process that you see at this point, the function at the time t, is very similar to the function at the epsilon, a very tiny bit of time step before, right? So this is not a weird assumption anymore, whereas it was weird assumption when we were dealing with SD. So this is a kind of very high-level illustration why this is working, okay? But if it's not very clear, no worries. I mean, it's not going to impact your understanding of DDIM. Just take it from my side. You can approximate this guy with this one. This is not a bad approximation, yes? Yes, definitely. I mean, in training, you don't use DDIM. This is only for in training, you always do time sampling, and you're right. You always sample, right? But the thing that you sample, you use it later as a label to train, right? The variant in the DDPM, you mean, right? Because in DDPM, when you are sampling, if I get very back here, yeah, here, whenever when you just computed the previous time step, then you add this guy, right? You always add one random thing. So this is the randomness that you have, but you don't have it here anymore, right? So you're deterministically computing the previous time. Sigma t, you mean? This one. Yeah, no worries. It's not exact. I mean, the formula you use here is not exactly the same, but right, you are getting it right. Eventually, you are trying to put that sigma t 0. But then instead, to make sure that somehow you are compensating for its impact, you're using, the previous, the next time, actually, time t estimation to somehow compensate for that. Okay. So, everybody's clear? So what you eventually do, you compute your estimate of the very beginning of time, then you use that one to estimate the previous time, and when you need to know what is the approximate of the direct noise of the previous time, then you just use whatever you have right now, okay? That's it. So now, if you do that, so you have this guy, and your x hat t minus 1 is going to be eventually given in this form, right? And then this one is a deterministic way of sampling. So you get your noise sample, your x capital T sample, the very last sample which you have drawn from Gaussian noise. Then you start to just, every single time, you start to first estimate the very beginning of time. Given that bad estimate, you try to estimate the previous time, right? So you denoise one step. And now you have a new version, a new denoise version. Again, you try to use it to estimate the beginning of time. You get that poor estimate, then you again compute the previous step, right? And you keep on going till you get to the very beginning. And every time that you do this, you're going to see that the estimate of the very beginning of time is getting better and better, right? So at the very beginning, the estimate of beginning of time is quite like your data sample, that x hat 0. When that t is very large, very close to capital T, this is pretty much noise, right? But as you reduce this value of t, this is going to get more and more close to what you want. Okay? Everybody's cool? So one key point that you should pay attention here, the DDIM is only a sampling algorithm, right? It has no impact on your training. So the training is exactly the same thing as we had with DDPM, right? DDIM is only helping us once we have trained the model to just sample from that model faster with less time steps. Okay? So that's only this. And typically what we do, we typically do exactly the one which I explained in the previous slide. So every single time you try to estimate your noise, then you use that one to get one estimate of the beginning of time, x hat 0. Then you use that x hat 0 plus the direct noise estimation to just go one step backward in time, and you keep going till you get to the beginning of time. Everybody's clear?